Welcome! Today, we will explore LeetCode problem number 1790, titled Check if one string swap can make strings equal. This problem challenges us to determine whether a single swap between two characters in one string can make it identical to another string. Let's dive in and tackle this step by step. In this problem, you are given two strings, s1 and s2, both of the same length, n. The task involves determining if you can make s1 equal to s2 by performing at most one string swap on s1. A string swap means selecting two indices in s1 and swapping the characters at those positions. If it's possible to achieve equality with one or no swaps, you return true. Otherwise, you return false. For the input format, s1 and s2 are strings of length n, where n is between 1 and 100. The output is a Boolean value indicating whether s1 can be made equal to s2 under these conditions. Let's look at some examples to clarify the problem. In example 1, s1 is bank and s2 is camb. Here, we can swap the characters at indices 0 and 2 in s1. After the swap, s1 becomes camb, which matches s2, so the output is true. In example 2, s1 is attack and s2 is defend. No single swap in s1 can make it equal to s2. Since the condition of at most one swap is not met, the output is false. In example 3, s1 and s2 are both kelb. Since the strings are already equal, no swaps are needed. This still satisfies the condition of at most one swap, so the output is true. These examples illustrate the variety of cases we need to handle, from swaps being required, to no swaps being needed, to cases where equality is simply not possible. The problem comes with a few constraints and edge cases to consider. First, the lengths of s1 and s2 will always be equal, and both strings consist of only lowercase English letters. For edge cases, if s1 and s2 are already equal, you return true. If there are more than two mismatched indices between the strings, it's impossible to make them equal with one swap, so you return false. If exactly two mismatched indices exist, you check if swapping the characters at those indices makes the strings equal. Finally, if there's only one mismatch or no mismatch, you consider that either no swap or one swap may still satisfy the condition. These constraints and edge cases will help guide the implementation of your solution. To tackle this problem, our goal is to determine if swapping exactly two characters in s1 can make it equal to s2. One approach we could consider is the brute force method. In this approach, we systematically try all possible pairs of indices in s1, swap the characters at those positions, and check if the modified string matches s2. While the steps are straightforward, generate all swaps and compare each resulting string to s2, this method is computationally expensive. The time complexity is n squared, because we evaluate all possible pairs of indices for a string of length n. Additionally, each swap might require creating a new string, which adds to the space complexity, making it n. Overall, while this approach works, it's not practical for large inputs, as it doesn't take advantage of the problem's constraints or structure. This inefficiency highlights the need for a more optimized strategy. A more efficient solution is the optimized approach based on understanding the problem's constraints. If only one swap is allowed, s1 and s2 must differ at exactly two positions or not differ at all. Using this insight, we can break the solution into clear steps. First, compare s1 and s2 character by character and record the indices where the characters differ. If there are more than two differences, it's impossible to fix the strings with a single swap, so we return false. If there are exactly two differences, we check if swapping the mismatched characters makes the strings equal. Finally, if there are no differences, the strings are already identical, and we return true. This approach is highly efficient, with a time complexity of n, as we only need one pass through the strings, and it has a space complexity of 1, requiring minimal additional storage. By directly addressing the problem's constraints, this method avoids unnecessary computations and provides a clean, scalable solution. Another viable option is an alternative optimized approach that uses frequency counting. Instead of directly tracking mismatched indices, we count the mismatched characters and their frequencies. The idea is to verify if the mismatches can balance out, meaning swapping the mismatched characters would make the strings equal. Like the mismatch tracking approach, this method has a time complexity of n, as we iterate through the strings once, and a space complexity of 1, since we only store counts. However, this approach can be slightly less intuitive because it requires additional logic to confirm that the mismatches align correctly for a valid swap. After comparing these approaches, we choose the optimized method based on mismatch tracking. It aligns more naturally with the problem's requirements, is efficient with O(n) complexity, and is simpler to implement compared to frequency counting. Understanding the problem's key observations helps clarify why the optimized approach is the best choice. First, if S1 and S2 differ at more than 2 positions, no single swap can ever make them equal. This realization eliminates the need to consider unnecessary cases. Second, when there are exactly 2 mismatches, we don't need to try all possible swaps. Instead, we directly check if swapping the mismatched characters would result in equality. These insights simplify the solution and ensure we focus only on relevant scenarios. When we compare the approaches, brute force is computationally expensive and redundant, requiring O(n)² time, while the optimized approach achieves the same goal in O(n). Although the alternative string counting method also has O(n) complexity, mismatch tracking is more intuitive and involves fewer steps. By leveraging these observations, the optimized approach provides a clear, efficient, and scalable solution, making it the ideal strategy for this problem. This problem challenges us to determine if 2 strings, S1 and S2, can become identical with exactly 1 swap of characters in S1. The key here is that the swap must involve exactly 1 pair of characters, which means strings that are already equal, or those requiring more than 1 swap, are not valid cases. To solve this, we start with a couple of straightforward checks. First, we verify that the lengths of S1 and S2 are the same. This is essential because swapping does not affect the length of a string, so any length mismatch makes equality impossible. Next, we examine the characters of both strings, identifying the indices where they differ. For this, we use a list called mismatch to store these indices as we traverse both strings. Importantly, if we find more than 2 mismatches during this step, we can conclude early that the answer is false, since more than 1 swap would be needed to align the strings. This early exit helps us optimize the solution by avoiding unnecessary computations when the condition is already violated. Now that we have identified the mismatched indices, the next step is to determine if these mismatches can be resolved with a single swap. First, we check the total count of mismatches. If there are no mismatches, the strings are already equal, so we return true. If there are not exactly 2 mismatches, we return false, as a single swap can only fix 2 incorrect positions. Assuming we have exactly 2 mismatches, we retrieve their indices, say I and j. To validate the swap, we check if swapping the characters at these positions aligns the strings. Specifically, we confirm that S1 I matches S2 j and S1 j matches S2 I. If both conditions are met, the swap will make the strings identical, and we return true. Otherwise, we return false. A key takeaway here is that a successful swap requires both mismatched characters to be exact complements of each other in the 2 strings. Additionally, this approach is efficient because we terminate as soon as we detect an invalid mismatch count or confirm that the swap is not viable. To implement this algorithm, we rely on a single data structure, a list called mismatch. This list efficiently tracks the indices of mismatched characters, and since we only need to store 2 indices, it adds minimal overhead. When analyzing the complexity, the algorithm is highly efficient. The time complexity is O(n), where n is the length of the strings, as we only make a single pass through the characters of S1 and S2. The space complexity is O(1), because the mismatch list uses constant space regardless of the input size. Let's consider some edge cases to solidify our understanding. For identical strings, such as S1 equals ABC and S2 equals ABC, the output is true since no swap is needed. If there are more than 2 mismatches, as in S1 equals ABC and S2 equals def, the output is false because one swap cannot resolve that many differences. For a single mismatch, like S1 equals ABC and S2 equals ADC, the output is also false, as one swap cannot fix just one differing character. Finally, a valid single swap example is S1 equals bank and S2 equals camb, where swapping the first and last characters of S1 results in equality. Let's walk through a concrete example to see the algorithm in action. Imagine S1 is bank and S2 is camb. We begin by comparing the characters of both strings. At index 0, the characters differ, B in S1 and K in S2.
We record this mismatch by adding index 0 to the mismatch list. At index 3, there's another mismatch, k in S1 and b in S2. We add index 3 to the mismatch list as well. At this point, mismatch contains 0, 3. Next, we validate the swap. The characters at these mismatched positions must complement each other. Specifically, we check if S1, 0, equals S2, 3, and S1, 3, equals S2, 0. Both conditions are true, swapping b and k in S1 aligns it with S2. Therefore, the output for this input is true, confirming that the strings can be made equal with exactly one swap. The provided code solves LeetCode problem number 1790 by determining if two strings can be made equal with at most one character swap. Let's break it down step by step. 1. Length check. The first step is to compare the lengths of S1 and S2. If their lengths differ, it is impossible to make them equal with a single swap, so the function immediately returns false. 2. Find differences. The diff_indices list stores the indices where S1 and S2 have different characters. This is achieved using a list comprehension that iterates through the strings and collects indices where S1, I, equals S2, I. 3. No differences. If diff_indices is empty, it means the strings are already identical, so the function returns true. For exactly two differences, if there are exactly two indices in diff_indices, we check if swapping the mismatched characters would make the strings equal. For this to be true, the characters at these indices must crossmatch I, S1, I, equals S2, J, and S1, J, equals S2, I. 5. More than two differences. If there are more than two mismatched indices, one swap is insufficient to make the strings equal. In this case, the function returns false. ### complexity analysis. Time complexity. The solution runs in O, n, where n is the length of the strings. This is because we perform a single pass to find differences and another constant time comparison. Space complexity. The solution uses O, d, additional space, where d is the number of mismatched indices, at most 2. This implementation is concise, efficient, and handles all edge cases such as strings of different lengths, identical strings, and strings with more than two mismatches. Here, we start by defining the method are_equal, which takes two strings, S1 and S2, as inputs. The first condition checks if the lengths of the two strings are different. If they are, then it's impossible for them to become equal with a single swap, so we immediately return false. Next, we initialize an array, diff_indices, to store the indices where the characters of the two strings differ. Along with this, we have a variable diffcount to keep track of how many differences we've found so far. Then, we loop through each character of the strings. If we find a mismatch between S1 and S2 at a particular index, we first check if there are already two differences recorded. If there are, we return false because more than two differences mean a single swap cannot make the strings equal. Otherwise, we store the current index in the diff_indices array and increment the diffcount. Finally, if no differences are found after the loop, it means the strings are already equal, so we return true. If exactly two differences are found, we proceed to check whether swapping the characters at these two indices will make the strings equal. We retrieve the indices from the diff_indices array and compare the mismatched characters. Specifically, we check if the character at the first mismatched index of S1 matches the character at the second mismatched index of S2, and vice versa. If both conditions are true, then the strings can be made equal with one swap, so we return true. If this condition is not met, or if there are more than two differences, the function returns false, as no single swap can make the strings equal in those cases. This concludes our implementation of the are_equal method. To solve this problem, we start by comparing the lengths of the two strings, S1 and S2. Here, both strings have a length of 4, so we know they pass this initial check. Next, we find the indices where the characters in the two strings differ. We compare each character at the same position in both strings. At index 0, S1 has the character B while S2 has K, so there is a mismatch. At index 1, both characters are A, so there is no mismatch. Similarly, at index 2, both characters are N, so no mismatch there either. Finally, at index 3, S1 has K while S2 has B, which is another mismatch. After examining all indices, we determine that the differing indices are 0, 3. This gives us the information we need to proceed to the next step.
Now that we have identified the differing indices, we need to evaluate whether swapping the characters at these positions will make the strings equal. The differing indices are 0 and 3, so we check the characters at these positions.
At index 0, S1 has B and S2 has B at index 3. This condition is satisfied.
Next, at index 3, S1 has K and S2 has K at index 0.
This condition is also satisfied. Since both conditions are true, we can conclude that a single swap between these indices will make the strings equal. Therefore, the output for this example is true. For this example, the strings are S1 equals ABCD and S2 equals ABC. First, we check their lengths, and since both are of length 4, we continue to the next step. Now, we find the indices where the characters differ. At index 0, both strings have A, so there is no mismatch. At index 1, both strings have B, so again, no mismatch. At index 2, S1 has C while S2 has D, so there is a mismatch. At index 3, S1 has D while S2 has C, which is another mismatch.
This means the differing indices are 2, 3, and we can now evaluate whether swapping the characters at these positions will make the strings equal. With the differing indices identified as 2 and 3, we now check whether swapping the characters at these positions will align the strings. At index 2, S1 has C and S2 has C at index 3, which satisfies the condition. Similarly, at index 3, S1 has D and S2 has D at index 2, which also satisfies the condition. Since both of these conditions are true, it is possible to make the strings equal with a single swap. As a result, the output for this example is also true. In this final example, we have S1 equals ABCD and S2 equals ABF. As before, we start by checking their lengths, and since both strings are of length 4, we proceed. Next, we identify the differing indices. At index 0, both strings have A, so no mismatch. At index 1, both have B, so again, no mismatch. At index 2, both strings have C, so still no mismatch. However, at index 3, S1 has D while S2 has F, which is a mismatch. This gives us differing indices of 3. Now, we evaluate whether it is possible to make the strings equal with a single swap. Since there is only one differing index, it is impossible to swap characters to align the two strings.
Therefore, the output for this example is false. To analyze the time complexity of the solution, we start by considering the individual steps. First, checking if the lengths of the two strings are equal is an O(1) operation since retrieving the length of a string is done in constant time. Next, finding the differing indices involves iterating through both strings, comparing each character pair. Since the strings are of length n, this step requires O(n) time. After that, checking the number of differences involves simple operations like checking if the list is empty or retrieving its length, both of which are O(1). Finally, validating the swap, if there are exactly two differing indices, involves constant time equality checks and a logical AND operation, which are also O(1).
When we combine these steps, the overall time complexity is determined by the most expensive operation, which is the traversal of the strings to find differing indices. This step is O(n), and since all other operations are constant time, the total time complexity of the solution is O(n). Now, turning to space complexity, the algorithm uses a list to store up to two differing indices. Since this list has a fixed maximum size, its space requirement is O(1). Additionally, the algorithm does not use any other data structures that grow with the size of the input. All auxiliary space, such as for variables, is constant.
Therefore, the overall space complexity is O(1). Let's look at the best, average, and worst-case scenarios for this algorithm.
In the best case, the two strings are already equal. Here, the algorithm simply confirms there are no differing indices, which requires a single pass through the strings, resulting in O(n) time. In the average case, the algorithm might find one or two differences, perform the necessary checks, and still complete in O(n) time because it only requires one traversal of the strings. In the worst case, where the strings differ in more than two positions, the algorithm still traverses the entire strings to find all differing indices, which again takes O(n) time. Thus, the time complexity remains linear across all cases. To better understand the efficiency of this solution, let's compare it to a brute force approach. A naive solution would involve trying all possible swaps between pairs of indices in the first string and checking if the resulting string matches the second string. This would require n² time because of the nested loops over the indices. In contrast, the optimized solution avoids nested loops by directly identifying differing indices in n and validating them in O1. Finally, the mathematical proof of the big O complexity confirms that the dominant operation in this algorithm is the single traversal of the strings to find differing indices. All other operations are constant time and do not depend on the input size. As a result, the overall time complexity is O(n), and the space complexity is O(1). One common mistake to watch out for is failing to handle cases where the strings have unequal lengths. Remember, if S1 and S2 are not the same length, it's impossible to make them equal with just one swap. Always check this condition right at the start. Another frequent issue is overcomplicating the swap logic. Some approaches iterate through all possible pairs of indices, which can lead to an inefficient n² solution. Instead, focus on pinpointing the mismatched positions and determining if swapping those alone resolves the problem. Edge cases are also a critical area where mistakes happen. For example, if the strings are already equal, or if there are more than two mismatched characters, you need to ensure your solution accounts for these scenarios. Additionally, duplicate characters can sometimes be mishandled. For instance, swapping identical characters won't fix mismatches, so it's important to validate whether the swap resolves the issue. Finally, don't overlook the constraints. Since the problem guarantees that the string lengths are between 1 and 100, your solution should be efficient enough to work within these bounds without unnecessary complexity. In interviews, it's important to emphasize the core of the problem, identifying mismatched characters. Once you've identified exactly two mismatches, swapping them to test for equality simplifies the solution and ensures it runs in linear time. Be ready to discuss edge cases, such as when the strings are already equal, when they are completely mismatched, or when repeated characters are involved. These scenarios often test your ability to think critically. The constraints are also worth highlighting. Since the input guarantees lowercase English letters only, you don't need to handle invalid cases, which keeps the solution focused. It's also helpful to communicate any trade-offs in your approach. While a brute force solution with n² complexity might work for smaller inputs, a linear n solution is more scalable and ideal for larger datasets. Lastly, understanding related problems can help you draw parallels. For example, problems like LeetCode 859, buddy strings, or LeetCode 680, valid palindrome 2, share similar themes of string manipulation with specific constraints, and discussing these can showcase your ability to connect concepts. There are multiple approaches to solving this problem, each with its own trade-offs. A brute force method involves iterating through all pairs of indices and simulating swaps to check for equality. While this is a straightforward approach, it's computationally expensive with an n² time complexity, making it impractical for larger strings. A more efficient alternative is the optimized two-pass approach. In the first pass, you identify the indices of mismatched characters, and in the second, you validate whether swapping these characters resolves the mismatch. This approach runs in n time and is well suited for larger inputs. Another method involves character counting, where you use a frequency array to track mismatches. While this approach can work, it often introduces unnecessary complexity compared to the two-pass solution. For most cases, sticking to the optimized two-pass approach offers the best balance of simplicity and efficiency, ensuring your solution remains clear and performant. Thank you for joining us. To wrap up, we summarized the key points of solving this problem and highlighted important takeaways. This problem is a great practice for string manipulation and logical thinking. We encourage you to try similar problems and continue sharpening your skills. Don't forget to like and subscribe for more coding content. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!